Buenas tardes, bienvenidos a esta nueva edición de la Conferencia Santaló, que es ya una tradición en la facultad. Si no me equivoco, y tal como me han informado, sería la 13ª edición de esta Conferencia Santaló, donde, bueno, pues desde la facultad se trata de apoyar la revista Matemática Complutense. De hecho, es un evento organizado conjuntamente por la revista Matemática Complutense y la Facultad de Matemáticas. Así que, bueno, pues quiero agradecer el esfuerzo en la organización, tanto del director de la revista, José Chuarrieta, como del profesor Leandro Pardo, que ha trabajado en la organización de esta edición. Y, por supuesto, agradecer al profesor Horváth que haya aceptado nuestra invitación. Y por supuesto, pues a los asistentes agradecerles su asistencia, y seguro que van a disfrutar con esta conferencia. Le dejo la palabra al director de la revista, José Chuarrieta.
Muy brevemente, gracias de nuevo por estar aquí. Desde la revista seguimos con mucha ilusión y mucho empeño en que la Conferencia Santaló siga siendo un evento importante de la Facultad de Matemáticas. Estamos ya, de hecho, preparando la del año que viene. Vamos intentando año a año traer a gente de primera línea. Para el año que viene esperamos poder contar con la presencia de Hélène Snold de la Universidad Libre de Berlín, en el área de álgebra, geometría y tal. Y bueno, pues agradeceros a todos vosotros por estar aquí, agradecer a los estudiantes, que veo que hay público de estudiantes. Creo que intentamos que siempre intentamos que esta conferencia vaya dirigido no solamente al público especialista en el tema, sino que sea dirigida a toda a la Facultad de Matemáticas y a los estudiantes. Y bueno, pues agradecer a Lajos Horváth por aceptar la invitación, y voy a pasar la palabra a Leandro Pardo, que va a hacer la presentación científica, creo que ya en inglés, y va a ser el moderador de la conferencia.
Thank you very much, Professor Arrieta. It is a sincere pleasure to introduce Professor Lajos Horváth to this audience. And I should thank the Dean of the faculty, as well as the editor in chief of Revista Matemática Complutense for this honor. As most as you know, Lajos Horváth is professor in the Department of Mathematics and Statistics of the University of Utah. He's an expert in mathematical statistics, limit theorem, nonlinear time series, non-parametric method, in probability theory, local time, log density, path properties, as well as in stochastic process, weighted approximation, invariance, and so on. His many authored and edited books, as well as his paper, more than 300, are well known. His paper has been published in the most important statistical and probability journal, Annals of Statistics, Annals of Probability, JASA, Biometrica, Royal, Journal of Multivariate Analysis, Journal of Statistical Planning and Inference, and so on. He's member of several editorial boards, like Journal of Statistical Planning and Inference and Journal of Financial Time Series. Professor Horváth plenary Santaló 2012 lecture is entitled Functional Data Analysis. Professor Horváth, please.
Thank you. So, thank you very much for the invitation. I turned it on. I am not really sure it is working or not, but according to my students, I am loud enough. Anyway, so I hope that it is working. Thank you again for the invitation. This is my second time at this university giving a talk, so it is a great honor to be back. Okay. I changed the title a little bit, okay, because the title now is exactly the title of the book what I published recently with Professor Piotr Kokoschka. So this is the reason for the change. Mainly what I would like to do, I would like to show some problems, some data sets, okay, about statistical inference, when the observations are modeled as curves, I would like to point out some methods. What kind of mathematicals can be used to analyze the data, and also I would like to see, okay, I would like to show you some consequences, okay, which came out from that one. There will be several pictures, okay, so all the pictures what I will show you, all the data analysis, they have been done by previous and present graduate students, okay, so don't ask me what kind of code I use. I didn't use any of them. All of them were done by my students. I'm very grateful for that one. Okay. So this is an example, okay, so about functional data analysis. What you are looking at essentially, those are the IBM stock prices that when they were traded there, and those are given for 3 days. So this is the raw data there. So when you look at it, okay, these are observations. There are several of them. To typically, on a good day, like in this case, okay, the second day, this is traded every minute. Okay, the stock price is there. If you would like to do some kind of standard statistical analysis there, you are looking at extremely high dimensional data there. So the dimension is very, very close to 600, 700 there. Okay, and the biggest issue is that, roughly speaking, the design matrix is singular. So using some kind of a standard method is not very easy to do this one here. So what is done in a case like, and again, so it can happen that there was a trading on some kind of a second and on the first day, but nothing is happening at this moment on the second day there, yeah? These are very, very irregularly spaced data there. So in case of functional data analysis, those points essentially just connected, okay, so like that one, and in this case we talk about, okay, a curve there, and those are essentially, okay, what we talk about the price curve, and this is what you will get nowadays on the internet. So the internet, when you are looking at stock prices and so on, you can see it, okay, coming up when something trading was done there. In this case, we are looking at 2 prices there. This one here is the IBM price, okay, and the other one is the Walmart stock price there. In this case, one of the interesting questions is, if you look at this one, okay, they are tend to move, okay, essentially in the opposite way. So the natural question is it true or not? That somehow there is a fundamental different behavior in case of the IBM, which is essentially like some kind of a high-tech industry stock there, or Walmart, okay, which is a staple, this is a consumer type of stock there. The other interesting one, data which has been studied lots of in the literature there, and these are the so-called magnetometer readings, okay, and there is the reference when this was connected there. This one is a very, very large data set, and essentially those magnetic storms, those are observed. Essentially more than 200 locations on the Earth, yeah? And essentially what people are looking at, the strength, the direction, and all kind of things about the magnetic storms there. The data is essentially which has been collected in the 50s. Originally, it was a data set which people in physics like to collect, okay, and analyze it. And this was essentially the first big collaboration between the former socialist and the capitalist countries there. Nowadays, it became extremely important due to the use of the mobile technology there. So when there is a storm coming, then in this case disruption, okay, in communication, cell phones, okay, but I would survive, but young people may not survive for a very long time. But there is much more problem, okay, like communicating with aircraft, okay, directing aircraft and things like that one. So it's still a relatively a very, very large project, okay, which is going on, and people analyzing it. There is another very nice aspect to that one here. This is essentially data on a ball there, yeah? So essentially not like two-dimensional data, but you have some kind of a very nice, okay, geometric aspect to that one. Okay, the next one is a very, very famous data set there, and I like this one very much because I think this is the first time when one of my graduate students understood that there is money in statistics there. Okay, what you are looking at, this one here, this is a Swedish company which is providing a handheld device mainly to see how much protein is in the beef. More protein, it is more expensive, yeah? So in this case, what they are doing is essentially they are using a spectrometer, and these are the absorption curves there. And the project was is essentially provide some kind of a method there which will be more accurate. Okay, if you are in food industry, is a very, very important one, because with this one, essentially using this machine there, you will get immediate readings there. Otherwise, the standard method was to cut out a part of the beef, make into a liquid there, measure it, and it took 2-3 days to do it, okay? And after that one is questionable, okay, whether this is a fresh beef anymore or not, yeah? So now this is done instantaneously. If you look at this one here, all of them are curves, but you can see that they have essentially the same shape, yeah? Okay, so this one here will be important later on. Okay, this one here is something which is coming from Spain there, and this is the pollution level on a given day, okay, and in this case those are functional curves there because this is measured essentially every 5 minutes there, yeah? If you look at this one here, this is some kind of a pollutant which measured, and you can see some typical feature there, okay, this is very, very high when people are driving and going home, yeah? Okay, going to work there, sorry, okay? And essentially it is typical in every country there. Okay, this is done in Europe-wide, having this machine everywhere in the name of clean air, and it's very important to see it. Like some kind of an intervention was done, it is working or not, when the intervention should be done there. If you're looking at this one here, that in this case the peak is around, okay, 9:30 there. In Austria, this is 8 o'clock. Okay, this is essentially much, much earlier. If you're looking at this one here, we have the same thing in Salt Lake City there. This is essentially peaks starting surprisingly at 7 o'clock and going until 10:30. Yeah, it's never that high, but it goes. Another one. The other interesting thing is that some people start driving, according to this one here, after 8 o'clock. Okay, I would like to say this when people are going home after work, it's a little bit late. Okay, going home at 8 o'clock there. Okay, so how to analyze a data like this one here? Okay, the model what we assume, we use a standard mathematical model there. So we assume, okay, that the functions, the random functions what we observe, those are square integrable functions there. Okay, so roughly speaking, okay, we assume that this random comes this element of a Hilbert space there. It is a standard mathematical theory that when you are looking at a function in a Hilbert space, okay, these are square integrable functions there, that this can be expanded, okay, according to any basis there. Yeah? So you can use whatever basis you would like to use. Okay, in the first part of the talk is essentially what I would like to do. We would like to replace this infinite dimensional, okay, infinite dimensional function with finite dimensional one. So what I would like to do is essentially I would like to approximate the infinite dimensional curve with a finite dimension like a d-dimensional one. Yeah? And I would like to have the best possible, okay, the best, in some sense, the best possible approximation. From a statistical point of view, what you are looking at the mean square error. So this one here, okay, this is just the L2 distance between the random curve, okay, then the corresponding d-dimensional approximation. And then, because this is random, to get the randomness, I mean, to computing the expected value, so this is just the mean square error there. So I would like to choose a basis just to have, okay, this distance become as small as possible. This is very natural, everybody agrees. At the end, when I talk about the prediction, this will be essentially the worst thing to do. Okay? Always depends on the data, what you have and what we would like to achieve. Only thing what we would like to do now, what we observe, try to essentially replace this one with something which has a simple structure there. Okay. How to choose the basis there? If you remember the Decatur data there, you can see essentially the same function being around. Yeah? So instead of using like the sine cosine as the basis there, it will not be a very good one because you can see what would be like the first function what you are using there. So how to choose the basis there? What we need to do is the following, okay, that first of all, we are using a one-dimensional projection there, and we would like to choose the function, okay, that the L2 distance will be as small as possible. Yeah? So we will pick the first element of the basis there. Then now we are using the first term and an additional one. Okay, the next one must be orthogonal for the first function what we picked there, and we are doing this minimization problem there. This one here is one of the basic things in Hilbert space theory, and also when you're talking about stochastic processes in Hilbert spaces there, that what you need is essentially you have to use the so-called covariance kernel or the covariance operator there. Since we assumed that the observations what we have, they have a second moment, this expected value here is finite. Okay, this is a well-defined function there. Okay, this function, of course, it will define an operator there, and since this is a positive definite symmetric function there, you can solve this problem there. You can to find the eigenvalues and the eigenfunction of this operator there. Yeah. Okay. So this means that according to this famous theorem there in real analysis there, then in this case this CTS, the covariance function, can be written in a form like that one, okay, lambda I phi I t phi I s there, okay, and this is converging in the L2 sense. And when we would like to have the best approximation for the functions, these are the phi i's, okay, what we need to use there. Yeah. So the basic observation is that whenever you would like to get the best approximation, then in this case what you need to use the elements, okay, of this covariance operator there. Roughly speaking, what you need, you have to solve this equation there, and you have to work with that one. Okay. Okay. So what kind of mathematical results you need to prove? When I will talk about the analysis of these curves there, sooner or later we will use the central limit theorem. If you ever seen even one single course, okay, in statistics there, the central limit theorem was there. This is one of the most basic ingredients. We will need something like this one in Hilbert spaces there, okay, and this is essentially the theorem, which is a very, very simple generalization of the earlier results there. So we assume that the observations are independent, identically distributed, okay, the observations are in L2, and then in this case the partial sums of these random variables can be approximated with a Gaussian random process there. The Gaussian random process will have mean 0 there, of course, because these observations, they have mean 0 there, and the covariance function of gamma n, this is the covariance function, okay, of the elements of these random functions there. This is the complete analog, okay, of the central limit theorem there. This one here is written in a somewhat strange way. Okay, what we say that you can find copies of the limiting Gaussian process such that the distance between this random function and copies of the Gaussian process, those are very, very close to each other in the L2 sense there. Yeah. The other thing what you need to remember, that when you are looking at this gamma n t, when n is changing, you are looking at different sample paths there, but the distribution will be exactly the same. The distribution doesn't depend on the value of n there, and our proof is a constructing one. Essentially, we are constructing those Gaussian processes there. A few consequences of that one. Okay, so one of them, when you are computing the square integral, this is converging in distribution to the square integral of the Gaussian process there. And in this case, just using that, okay, that this function has this covariance function CTS, and using the Karhunen-Loew expansion, we will have this very, very nice representation concerning the limit distribution there. This is just a weighted chi-square. Ni's, those are independent standard normal random variables, and in this representation, the lambdas are showing up, and those were, okay, the eigenvalues of the covariance operator associated with this covariance kernel there. This is based on the representation that when you are looking at this Gaussian process there, this Gaussian process can be written in a way like this one. You have standard normal random variables, you have the square root of the eigenvalue there, and you have the corresponding orthogonal functions there, which were the eigenfunctions, the eigenfunction of this covariance operator there. Now, what we will need, this is just the central limit theorem there. In this case, we would like to see that first of all, if you think about, okay, this data set there, okay, what I showed, for example, about the air pollution there. You would like to see if, for example, the mean curve is changing over time there. So this means that now it will be important which day you are looking at. So this, from a mathematical point of view, okay, you still have the xit there. T is the time during the I day there, yeah? But also essentially which day you are looking at, this is also changing there. So in this case, we have a two-time parameter process there. Okay, x means how many days we are considering it. X is running between 0 and 1 there. And t is the other parameter because we are looking at functions there. Okay, both of them in some sense time. Okay, t is the time inside of the I day there, and you are taking the summation with respect to the number of the days. Okay. Now, the approximation what we have, again, the limit result, is very, very similar what we had before. Okay, only thing that we have essentially, again, Gaussian processes there, but no, you have two parameters, x and t there. Yep. Okay. In this case, again, the distribution of this process doesn't depend on the end there. Okay. The Gaussian process is completely determined by the covariance structure. The mean is 0, and when you are looking at the covariance, this is the previous covariance what we had there. So this is essentially coming what kind of expected value you have, xit, xis there. This is measured by CTS. And the other one, okay, this is the minimum x and y. So this means that you are looking at some kind of Brownian motion time behavior with respect to the other process there. And this is the representation. If you look at this one here, this is completely similar what we had before, but instead of the normal random variable here, so here you have the standard normal random variable before, what you are looking at is essentially a Wiener process and the standard Brownian motion there. It's very, very similar what we had before there, okay? Only thing what we are looking at is, again, this one here is an infinite representation, a relatively simple one in terms of the independent Brownian motions or Wiener processes, these orthogonal functions which are coming out from the covariance kernel, and then you have these eigenfunctions there. So the point is that the classical theory, what you may have heard about the partial sums of random variables on the real line, okay, and the Donsker theorem with convergence type results there, those will get through in Hilbert spaces in a relatively simple way there, okay. As Dunford and Schwarz start, okay, in the famous book at the beginning there, every Hilbert space can be approximated extremely well with finite dimensional spaces there. And this is happening in this case there, so even we have this summation there going to infinity there, but nevertheless, okay, the method is exactly the same, that we are approximating everything with finite dimensional spaces there. So what is the problem for statistical inference? So whatever we would like to do there, okay, we need those eigenfunctions. So if you remember, the convincing argument is that whenever we would like to replace the infinite dimensional data, okay, because now we considered everything is a curve there with finite dimensional one, we would need those phi i's, okay, the eigenfunctions of the covariance operator there. But we do not know them, okay, because A and C is unknown. So therefore what we need, we have to estimate them, okay, from the random sample there. So how to do this one here? We are just computing the sample mean. This is just the average of the observations there. So this is the sample mean of the curve, which is a curve there. And in this case, this average, okay, this is just the empirical covariance operator there. This is like, okay, the covariance matrix, if you have seen higher dimensional statistics there. So what we know is the following. This is just the low flash numbers in Hilbert spaces, that the distance between C and hat and C goes in probability to 0 there. So this means that they are relatively close to each other. So what the natural thing in this case is just to compute, okay, the theoretical eigenvalues and eigenfunctions there. So instead of having the C there, the theoretical one, no, you have the estimators there. This is again the standard technique in statistics, okay? Then you are using a plug-in type techniques there. You do not know the C, so therefore you are using an estimator for that one. and you solve these equations like that. Okay. What do we get out of that one? And this one here is copied from Dunford and Schwartz. So first result what we have, if you are looking at if the eigenvalues are different, then in this case when you are looking at the difference between the theoretical one and the estimated one, the difference between the two is going to 0 in probability. Yeah? According to Dunford and Schwartz, the famous book there, when you are looking at the difference between the eigenvalues and the eigenfunctions, these are bounded by, okay, the difference between the corresponding operators there. The estimator of the eigenfunctions, okay, this is much more difficult. The reason for this one, if you go back to the definition, the eigenfunctions are not uniquely defined. Yeah? They are uniquely defined up to a sign there, even when the eigenvalues are different. So from a statistical point of view, this is a major issue there, okay, because you do not know whether, okay, so your estimator, what is coming out from this one, okay, this is related to phi to minus phi there. So only thing what we know, that whatever is the solution of that one, it is close to the eigenfunction of the kth eigenvalue there up to a sign there. From a statistical point of view, okay, what we need, that everything must be invariant later on, okay, for the sign of these operators there. So you need some kind of a property like this one, that nothing will depend on whether you are using, okay, here phi I or minus phi I there. If you do not simulation, if you do computation in R there is a very, very interesting thing, what is very, very easy to see it, that you will compute like what is phi 1 hat using 100 observations there. Yeah? And you will get a nice curve. Then you add an additional observation, and surprisingly, according to the software, now the eigenfunction will change sign. It will be nearly the same, that for some unknown reason how people wrote the software, now it looks completely different what was there. It is essentially flipped. So let's start with some kind of a statistical problem there, and I will show some examples for that one concerning, okay, the global warming. The model what we are looking at, that we have a curve, there is some kind of an expected value there, so this is not random, and some random error term there. What we would like to see, that the mean curves are the same in the L2 sense, so they be different essentially on a 0 set, against the alternative that there is one change there. Here I assume for the sake of simplicity one change, but you can assume essentially more than one, and the same thing would work there. The typical things which is suggested in statistics and coming mainly from quality control, that testing a null hypothesis like this one, this is based on the so-called cumulative sums there. What happens in this case, it is computed the total sum, so this is just the average, okay, if you're looking at the sum of the xi divided by n, to the sum of the first nx observations there, yeah? Okay, so first of all, okay, this one here there is a change there. This is estimating a linear combination of the mean before and after the change. In this case, if you are looking at this one here, until you will reach with nx the time of the change, this is exactly, okay, the mean, whatever happens before the change there, so you will have a significant difference between this sum here and this sum here there, yeah? This one here is related to the maximum likelihood method in case of normal observations. This one is a very, very nice and very important techniques there, and due to this importance, books are written about that one, how to use the cumulative sum methods in practice there, okay, based on data there and observations there. So based on, okay, what you can show, if you use our previous results there, then you can see how this looks like, this SNXT there. This is essentially what we had before the partial sum, minus when you take the summation when x is 1 there. So this means that asymptotically, okay, this SNXT there, which roughly speaking, okay, just bridge down or close down at 1 type process there, you will see that this is relatively close to a process like this one. First of all, under the null hypothesis, the mean doesn't matter, it washes out. Okay, this is just a simple algebra there. And in this case, okay, this is just the partial sum minus the partial sum at 1 there. So this one here is asymptotically under the null hypothesis. This is normally distributed there. And you have this very, very nice, okay, representation again for the covariance kernel there. The interesting thing is that CTS is showing up there. And in this case, you are looking at, again, a recognizable part there. And this is just the covariance function of a Brownian bridge. Okay. So the limit now can be represented like before. Instead of difference between the previous one, then instead of independent Wiener processes, you have independent Brownian bridges there. So if you are looking at the supremum functional with respect to x, or the Kramer from Mises, so this means that the integral functional with respect to x, then in this case you can have all kind of nice limit theorems there. So what is the problem there? If you look at this one here, if you are looking at this process, okay, which is showing up, it is not distribution free. Yeah? Look at this one here, the lambda I, it is there, and we do not know that one. Okay? This is part of the covariance function there. Okay. What is suggested in this case is the following that first of all, this is an infinite sum. Typically, it is converging extremely fast there. So what we are doing here, we are just replacing, okay, with this one here with d there. So this means that the infinite sum, we are keeping the first d terms there, and then the unknown lambda I, this is replaced, okay, with the corresponding estimator there. When we solve this, this empirical integral operator, we not only got estimators for the eigenfunctions there, but also those are come out very, very nicely, the estimators, okay, from the lambda i's there, this lambda I heads there. So if d is large enough, then in this case, this term here, now you can compute very easily. Of course, we know what is the distribution of the Brownian bridges there, especially the square integral, and also, okay, the distribution of this one. We can get a very, very good approximation concerning the limit there. The question is how to choose the value of d there. And the natural technique is, okay, that if you are using d terms, it should explain a large part of the randomness from the whole data there. When you are taking, okay, the sum of the lambda i's, this is essentially, okay, the square integral of the variance of the limiting process there. So you would like to have, okay, so this large enough, then in this case you will get that this is 0.9, 0.95. So like 90% of the randomness in the data is explained by the first d vectors there. Okay. So in this case, okay, so you will have this approximation for that one. So in the examples what I show you, that in this case it turns out that d will be 8. On the data which I show you, in case of the Decatur data, when you're talking about the beef, not surprisingly, even 1 will explain 99% randomness in the data there. You were looking at the same curves, okay, in some sense. Essentially there, in the data when I talk about the temperature, d will be 8 there. So this means that essentially the infinite dimensional curves, those are reduced to 1, 2, and 8 dimensional curves there. There is one issue, okay, what will happen if you have under the alternative? It turned out, okay, that under the alternative, using this method, you are always getting a finite value there, whatever happens. Yeah? So this means that, okay, that even it got no relation whatever happened there, it's always a finite value, and since under the alternative, the cumulative sum is going to infinity at the rate square root of n there, you always reject. So roughly speaking, you do not have the problem that if you have the alternative, then in this case, okay, then you are getting some kind of a too big critical values there. Okay. The other one, it is the projection method, and this is coming, okay, from Ramsey and other people there. What they said is the following, okay, that pick a d there, and what you do is essentially you're projecting everything into the d-dimensional space there. If you are looking at this one here, okay, this is the observation minus the total mean there, and this is projected into the direction of phi I head there. Yeah? So this means that what we are doing in this case, we are projecting the difference between the observation and total mean into a d-dimensional space there. Again, if d is large enough, then in this case this is supposed to be close enough, okay, to the, yeah, it should provide a good approximation for the limit for the original process there. We have the lambda I had there, and this is coming from the statistical fact that when you compute what is the expected value of this random variable here, this is exactly, okay, related to the lambda k there, and this is just an estimator for that one. Yeah. So what you are doing in this case, okay, so you are doing, okay, this projection there. So these are very, very easily computable, okay, just some kind of inner product integrals there, and those are divided by the corresponding eigenvalue there. Not surprisingly, okay, so in this case what you will get, that this partial sum is converging now in D01 in the function space sum of the squares of Brownian bridges there. It's very easy, okay, if you go back, okay, what is happening here and what happened in the previous one. Okay, so when you had these lambda i's, now those are divided in the definition of the statistics there. Okay, here you have that, in the other one you are divided with this one, and this will be, okay, in a different part there. Yeah. This one here is, of course, come with a warning there. If one of the lambda i's are very, very small, roughly speaking, okay, this part will be not a very, very good one. Okay, so you have to be very, very careful not to have too many terms there. Yeah. So people think if you have a larger d, then in this case everything will get better. This is not the case. It's essentially an introducing more and more noise there is getting good and getting worse and worse. So here is a famous data set there. Okay, and this one here is the temperatures in central England going back 228 years there. Yeah. So the question is whether, okay, global warming is real. Okay, there is a very, very long, big discussion and lots of money floating around. Okay, the easiest way for a government to provide research, okay, looking at global warming instead of doing something real. Okay, it's much, much cheaper there. See, if you look at this one here, okay, so this is essentially a daily data what was collected in England for that many times there. And if you look at this one here, this is essentially the real observations there. The continuous curve, okay, what you are looking at, this is just a smoothed version of that one, okay, using splines. And these are what you are looking at, okay, these are just the monthly averages there. So the natural question is, okay, whether the mean curves remain the same during these 228 years there, or something happened, okay? Like the temperature is really increasing, in this case there should be some kind of a changes in the mean there. Okay, here is the conclusion there, what comes out, okay, from that one. Okay, there. Two methods were used. One of them, okay, was using this monthly data there, when D is 12. Yeah? Then in this case, okay, what you are looking at is the beginning of the data, and these changes we found there, this one and that one here. Yeah? If you are using the functional data, so you are looking at this observation and curves there, then in this case 8 projections explains 97% randomness in the data there. Yeah? In this case, okay, so first of all, whenever you had one change there, now this is essentially split into 2 there. Yeah? And the other thing, okay, what you can see, that there is a change, okay, after 1992 there. Yeah, okay. So this one here is essential. There are several changes there, and we can look at, okay, how the data looks like. Okay, I can see only, okay, so 3 curves there, but there is a 4th one, okay, which is going around there. If you look at it, okay, so first of all you can see that there is some kind of increase in the temperatures there. Yeah. So these are essentially getting, okay, warmer. Those are not, I would say, okay, so uniformly going up there. So first of all, when you have the lowest temperature, this is not at the beginning of the data. Yeah, this is not in the beginning of data. There is essentially some kind of a period like that one. Yeah. So what happens essentially in this case, that when they started to collect the data there, it was a warm period. Yet then in this case, okay, cool down. It started warming up. And then there is essentially another warming up which is started around, okay, so 1992 there. It is a relatively short period there, yeah? This is the England data there. If you go back and you look at the same data set, for example, in case of the Czech Republic Prague there, this period will be there, but this will be a cool down period in Prague there. And this is a very surprising thing, okay, when England is warming up, why Prague is cooling down. Okay, so this comes essentially after 89, and this is when all those heavy industries went bust in Prague there, so the pollution is completely gone. By 1992, and in this case keeping it warm, now the city is essentially cooled down a little bit due to that one. So this was the IID case, and now I would like to talk a little bit when you are looking at dependent data there. My motivation, a lot of things what I showed is coming from business, and of course in business statistics there is dependence there, and very soon we would like to make predictions, okay? Like what kind of stock prices we should have the next day. We need some kind of a model for dependence in L2. So one of them, okay, what I'm showing up there, this is the autoregressive one process there in case of functional data there. This is very, very similar how an autoregressive one process is defined there, but instead of just multiplying the previous observation with a constant there, okay, now what you are looking at this one is a function. So roughly speaking, you are taking out the average with respect to kernel, what happened on the previous day. The main thing what we would like to know in case of time series there, whether what you defined, it has a stationary ergodic solution there, and for this one it's relatively easy to find conditions like that one. So this is well understood, that one. Okay. Similarly, you can define the autoregressive moving average, okay, with parameters PQ there. This is just formally defined as the previous one. When you have the number, now you have an integral operator there. Okay. For this one here is essentially using the contraction principle. It's very, very easy to find sufficient condition that an equation like this one, it will have a stationary solution, but to have the complete theory what you have in case of ARMA PQ process, okay, on the real line, but in case of vectors is a very, very difficult one, okay. Those are related to solutions of certain equations there, and now you have the coefficient functions much, much harder there. These are parts of the so-called functional linear processes. Okay, these are just an infinite sum when you are looking at, okay, these averages using these kernels there. Further one, and this is what is used and we like very much, and those are the volatility processes in L2. One of them is the functional arch process there. The functional arch, okay, if you look at this one here, the recursion is not really, okay, in the process there, but in the volatility of the process there. If you look at the definition like that one, epsilon kt is a random variable, and when you are looking at, okay, the volatility or the variance term there, this is given by a recursion like that one. In case of the arch process there, the volatility at times k there, it depends on the value, okay, of xk in the previous time period there. So it tells you that you will have a large volatility, okay, if you had too large or too small prices there. Yeah? Okay? It tries to explain there's some kind of a dynamics behind it. The generation, this one is the Garch 1, and in this case when you are looking at the volatility at times k there, it depends on the previous price, okay, and also on the previous volatility there. With this one you can have the so-called volatility clusters there, okay. There are excitement on the market there, and they will hold a certain period, and having the volatility there, okay, it builds it up in some sense, and then everything collapses and it goes down something, okay. There is much less volatility here and there. The other interesting part, that what you observe, okay, is xt there, yeah? Okay, xt by definition, okay, those are uncorrelated with respect to k there. So this means that if you would like to do prediction and so on, this will be very, very unpleasant. Okay. This one here is just some kind of a general definition when you would like to do that. Essentially, instead of working with each of the processes there, what I mentioned, all of them are elements of the so-called Bernoulli processes there. Yeah? If you look at this one, all of them can be written in a form like this one, that xk is some kind of a functional of independent, identically distributed random variables. Yeah? Okay? All of them can be written in a form like this one. And then the dependence that these are weakly dependent processes means that when you are looking at how xk behaves, what really matters is essentially those who are very, very close to the term k there. So if you are replacing the tail of xk there, then in this case the tail doesn't matter. Yeah? Weakly dependence is very often used there if you would like to talk about prices and so on. It doesn't really matter what happened 100 years ago. Okay? This is supposed to die out, and this is a model like that one. Okay. Okay, this one here is essentially just the central limit theorem for dependent processes there. It says that, again, the partial sums of those dependent random variables there, they will be asymptotically Gaussian. Yeah? Okay, if you are looking at the minimum x and y, this is what was before, but there is a different object, okay, which is showing up there. This is the so-called DTS. And this one here is the long-run covariance function there. This is very, very similar what you have in case of weakly dependent random variables there. Then it should be the long run, okay, covariance there, and now you have the long run covariance function. Structurally, there is very, very little difference. Okay, what we have seen before, the only thing what you have, that instead of the C, now you have something which is defined as an infinite sum there. So if you would like to go there, okay, the theory what we discussed, the natural thing, okay, what you need to do, you have to estimate this D instead of the C there. Yeah? Okay. I do not want, because I'm running out of time, I do not want to spend lots of time on it. This is the analog, okay, how it was done in case of real value data there. You are looking at, okay, the sample, the covariance is there of lag I there, and you are looking at a weighted sum of that one. The idea is the following, okay, that in the definition of D, you have an infinite sum there, yeah? But you will not have ever a lag when the lag is larger than n. So this means that you have to taper it out there. You do not want to have, when you are estimating the long-run covariance, that you are using a term there, okay, which based on 2-3 observations there. Those are not good there. So this is the reason, okay, why this function is there, that giving weight mainly to the functions, okay, which are relatively close to the center there, and when each is getting larger, then in this case, essentially, you are having more longer and longer legs there. This is a standard technique in time series analysis there. The result is that what we said, you will have exactly the same results there, okay? So whenever you are looking at this D n hat instead of C n hat there, and essentially all the results what we discussed so far, it will get through there. Yeah? No problem with this one here. Essentially, whenever we use the C and estimate it with C n hat, now you have D, and we can estimate with D n hat there. So structurally, okay, very, very little difference there. There is an unknown parameter which has never been there, and this was the function, this was the parameter h there. And how to choose this one here? There is a very, very large literature about the literature there, about that one. Lots of people written about in the real valued case there. There is no solution that one and never will be. Okay? So roughly speaking, the optimal age will depend at least 7-5 different things there, okay, which you do not know. You know what would be optimal, but you cannot do it. What we did, we suggested some kind of a data-driven estimator there, okay, and I will just show some simulations for this one, how it is working out. So this is our estimator for this D. This is this D n hat. This is 100 observations. You have 300 observations there. Okay, this is 500 observations there, and here is the limit. Okay, so this is what we wanted to get. So this means that essentially it is going relatively well into the right directions there. When the observations are 500, okay, then in this case it looks relatively good there. I am talking about, okay, so our motivation was financial data, and having okay, 500 daily observations is nothing, because you are talking about 1.5 years. Okay, so it's a relatively small one. These are the cumulative intraday returns, how they look like. Okay, and in this case, okay, when you are looking at this one here, this is the estimator. Yeah. If you look at this one here and you compare to the previous one, okay, there is a very, very big similar to that one. Roughly speaking, okay, this one here is very, very close when you are looking at the sums of uncorrelated random variables there. And this is converse, is essentially when you are talking about returns, those are Gestalt processes there and those are uncorrelated. Okay, I will skip the two sample means there because I don't have the time. Okay, and I talk about the function analysis of variance because this is related what we did before. Now, we already talked, okay, so how we are looking at the data there, and the inference was whether the mean was the same or not. This is a little bit is the same. What you are looking at in this case is the following. Instead of one population, we are looking at k populations there. So think about, for example, okay, those curves, okay? What I showed, okay, this was like the how much pollution, okay, you have in one location there. In Madrid, this is measured at 50 locations. Okay, so in this case, okay, k is 50 there, and the question is what you would like to see, whether those means are the same or not. This is the null hypothesis. So roughly speaking, okay, if you are driving in Madrid, then indicates that is essential pollution is essentially the same. Okay, I don't know whether it is true or not. Okay, in Salt Lake City is essentially it is the same everywhere because we are inside of a valley. When when it's essential the pollution gets in during the winter, it will not get out. Okay, and this is very, very important observation. This is the same there. In our case, you are talking about serious money there. We have snow and we would like to get rid of them. There are two possibilities, okay, what to do with the snow when you would like to drive. You put salt on it. Okay, this is cheap. Salt is cheap. Okay, the problem is that this is essentially providing the particles what you are breathing in. So roughly speaking, putting cheap salt is very bad for you. Okay, this is increasing the bad particles there. What is very, very good is some kind of a calcium based, and essentially this somehow puts down, okay, into the ground the very, very the bad particles, the small particles which would go into your lung there. The problem is this one here is 100 times more expensive than salt. So they only use it, okay, when we are ready to die. Okay, from this one here, so know it that whether we reach this level is very, very important. Yeah. Okay, so we would like to see whether this is same or not against the alternative that this is not the case there. So these are essentially the curves. Why is a difficult problem there? Here you are looking at three populations there, and the question is whether they have the same mean or not. Yeah? One of them is certainly different, okay, because essentially it's going up and down at the end there. And then in the middle one, okay, you are looking at all kinds of curves here and there. Just looking at visually, it's very, very difficult to see that you are looking at the same thing or not. If you put in the mean there, then in this case you can see that these are essentially the same. Yeah? These are based on 50 observations there, so you are looking at the same things there. So what we would like to do, we are using the projection method that we will essentially put everything into a finite dimensional data set there, finite dimensional space there. Again, dependence is allowed inside of each curve there, so we are using this estimator for the long run covariance function there. Okay. This is the same estimator what I already discussed before. Here the issue is, again, if you had analysis of variance, then when you assume the mean is the same, then in this case you can use the mean which is based on the total population there. Yeah? But this is only estimator for the covariance if the null hypothesis is correct. Or in this case you can put the average only what you have in the ith population, which is always consistent. Yeah? Regardless whether, okay, the mean is changing one population to the next one. I put this one in red there, because in this case, okay, if you put this one here, even if you are using one projection there, you will have, okay, absolute power under the alternative. Yeah? So if there is change in the mean there, and you are using an estimator which is not consistent under the alternative, then in this case you will reject the null hypothesis because it is not correct. So this is essentially the way to go in this case. Okay. These are just the definition of the statistics what you are looking at. Again, you are doing these random projections there computed from the data there. And these are just the standard quadratic form, okay, for the test statistics, what you may have seen when you are working, okay, with multivariate analysis of variance there. So you have this normalization using the eigenfunctions and so on. The basic issue in case like this one, that you cannot assume that the covariance matrices are the same for the projections there. This was in the previous curve there, is essentially when you were looking at the different colors there, they had different covariance functions there. The mean was the same, but the covariances were different. Okay. Okay, you will have the same thing what you have in case of analysis variance, that the limit statistics will be a chi-square. D is the number of the projections, and K is the number of the populations there. So this means if you are doing the same thing, okay, using the projections there, then in this case you can go back very, very nicely, okay, what you learned in classical analysis of variance. Okay. So here is the example what I wanted to show, because again it's very, very important, okay, how to deal with energy there. This is electricity demand in Adelaide, Australia there. Don't forget, okay, energy is very, very important. You would like to have it. The problem with energy, it cannot be stored. If you have it, you use it. If you are not using it, that it will be lost. So it's very, very important to see some kind of a pattern, how people are using it and when they are using it. See, in Australia, this is what they collected there. Is a very, very long project there. So it's going from 1997, 2007 there. It is done daily, and they are using, okay, half-hour data there, at least what we obtained. So each day they have 48 observations there. Okay. What they are looking at, okay, UNT, this is the electricity demand at time t there on day n. What they are using is essentially this log difference, the log difference demand curves there. Okay, so I would say whoever wrote the program and this project for the electricity company probably had a course in finance, because this is equivalent, okay, to the log return, okay, and this is what they are using there to model the data. So this is how the data, this is the demand curves look like, okay, showing the same pattern there, and this is essentially when you are looking at the different curves, what you can start is essentially all of them, though by definition, start at 0 there every day, okay, they are scaled back to 0. So what kind of problems you have, okay, with the data there? So first of all, when you are looking at, there are the 4 seasons there. So in the data you are supposed to see, of course, some kind of a seasonal pattern there. There is the summer, okay, which is December, January, February in Down Under. Then you have the fall, winter, and spring there. So the first step, what was done, the data was divided, okay, into those sets there. And we wanted to see if there is like, okay, some kind of a seasonal variation, okay, here. It turned out, okay, that what you are looking at, this one here, okay, these are the number of the observation, but you have the fall, summer, and those, these winter months there. Yeah, okay. So these are essentially when you are looking at the averages there. Again, if you look at this one here, if you are looking at the spring and the fall, those are essentially the same. Yeah? There is very, very little difference there. And statistically, essentially, these are the same curves. So those are statistically the same there. If you are looking at, okay, the summer, and also when you are looking at the winter curves, now those are completely different. So this means that in this case, you can put the data essentially into 3 sets there. You have the spring and the fall, which is the same. And then you are looking at the other months there. Okay. Okay, if you, yeah, this essential is collected with the corresponding levels there. The next thing, what you are looking at, the daily variation there, okay? So you pick one of the seasons there, And in this case, we are trying to look at this one, okay, how it is behaving, okay, looking at the different days and so on. So roughly speaking, okay, what we would like to see, whether, okay, that the demands on weekdays, those are the same what you have on the weekend there, yeah? And we are hoping it will not be, okay? And here is, okay, what came out, okay, from the data set there. These are essentially the curves what you are looking at, yeah? And these are the weekdays. All weekdays are the same except Friday, okay? So Friday around 2 o'clock, it looks like people in the light, they stop working already, okay? They are essentially start behaving like some kind of a, okay, day, and this is very, very, okay, similar to the pattern what you have essentially on Sunday there, yeah? And similarly, when you are looking at the other curve, okay, that the Saturday curve there, they have different patterns there. And this is a very, very interesting one. So roughly speaking, okay, so demand for electricity is essentially tapering off in the middle of Friday there. So roughly speaking, essentially, it's not worthwhile to produce as many energy what they are doing on weekdays. People are not really working anymore. The other thing, okay, what you are looking at this one here, then when you are looking at the demand on Saturday and Sunday there, those are different, okay? So demand on Sunday is much less, okay, what you are looking at, okay, on Sunday there. The explanation for this one here, that okay, then this is typically people are not at home on Sunday, okay? So this is the reason why they are using a little bit, okay, less energy there. And then Sunday, okay, they are at home, and roughly speaking, okay, they are heating or using air conditioning and things like that one. I wanted to, at the end, to show a few problems there. I always assume when I talk about the data there that I had, okay, stationarity there, yeah? And this is a very nice and interesting question, whether when you are looking at the curve, those are really stationary or not, yeah? The other interesting thing is that we're always using, okay, this dn hat, the estimator for the long-run covariance function, what is the distribution of that one? When you are looking at essentially IID case there, and you are looking at the estimator for just the covariance function there, this is well understood. This one here is a very, very difficult one, and this is the problem with the prediction there, yeah? If you are looking at the prediction there, the problem is that it can happen there that whatever you have here in the coefficients there, these are very, very badly predictable, yeah? This is an infinite series there, and it can happen when you are looking at like the first 10 coordinates there. Those are uncorrelated with respect to time there, and whatever is really providing the correlation between the previous observation, this is coming much, much later. So this means that if you would like to use the prediction there, it may not be the best thing essentially to use the basis what we use so far. So roughly speaking, okay, when you would like to do the prediction, you would like to have a basis which is essentially predictable and work with that one here. Okay, of course you cannot assume that first of all you can predict 100% randomness what you have the data there, a smaller percentage, but this is what you would like to capture when you are choosing the basis there, that in case of the prediction there, roughly speaking at the basis there, those are essentially, they got the coefficients which can be very, very nicely predicted from the data there. So it's a very nice and very interesting question, okay, like how to do some kind of a prediction there, okay, which is essentially working and relatively doable, and even computationally is fast, okay. In a lot of cases, okay, it can happen there that even xit is observed, for example, when t is 1/2, and you would like to make the projection, okay, when t would be 3/4, yeah? What will happen, okay, like 3 hours later that? So these are very nice and very, very interesting questions, and people would working in finance and business, yeah, they would like to know more about this type of predictions there. So thank you very much.
from the point of view of the statistical inference, all the two methods that was speak about the regression method or the Spanish functional method is better.
In general, the fully functional method, okay, it should be better. Because the reason is you do not have to choose in advance how many predictions you are using there. Yeah? The problem is when you are doing the fully functional approach there, it can happen the unknown covariance, okay, long run covariance and things like that one, they will be part of the limit results there. So this one here, okay, using the fully functional method, it is done by several papers, okay, in Spain. It's a very, very popular thing how to do this type of statistical inference, but in this case you need some kind of a resampling. The resampling can be done very, very easily when you have independent observations there. When you have time series, then in this case everything will be much more complicated, okay, and much, I would say, less reliable there. And the other thing is, okay, so in a lot of cases when I mentioned, it should be done sequentially. Like first of all, when I talk about the pollution, okay, then like it reaches some kind of a level there, then in this case it should stop and send out some kind of a signal that something should be done and so on. And in this case, of course, okay, to attach significance level to them, you cannot really do resampling, okay? Resampling requires time and things like that one. So in this case, okay, in a situation like this one, this may be better there, yeah? But if you can write, okay, very, very fast programs, okay, doing this and that, in general, okay, the fully functional should be way, way better. Thank you. Yes?
In your analysis of the data that we have, can you see that there is a global warming?
Okay, so the answer for this one, okay, the answer for this one here is yes and no. As a good statistician, I never take sides, okay? What you can look at it, okay, so like when you are looking at the European data there, especially in Central Europe there is some kind of a pattern which is going on there, okay? So first of all, in Central Europe, two types of things are essentially fighting each other. One of them is like what you have in for example, okay, Netherlands. Everything is nearly the same, okay? Nothing is too cold, nothing is too hot, yeah? And then you have the so-called continental temperature, like what you can have in Ukraine. Very, very cold winters and very, very hot summers there. And somehow when those things, okay, differ from each other, this is moving around there, yeah? Okay? It can be, okay, so first of all, this should be the temperature data that even having 228 years, okay, this is not a very, very long one, yeah? You can see all kinds of changes. Whether those are changes there, yeah? But whether those were man-made or those were natural things, it's very, very hard to say that one, yeah? I am very, very big supportive, okay, that global change is real in some sense because I like, okay, cleaner air. Okay, when we live in Utah during the winter, when we look out from our window, we can see the red air over the city there. So having a little bit, okay, better air due to global warming, it would be nice. Okay, so something like that one here. The problem with the global warming, when people go back and essentially they collected data, those are not real measurements there, yeah? Okay, and from that one, what they looked at, okay, like sea ice and things like that one, they attached the number to it, saying that this was the temperature. Well, okay, what is the variability in this one is hard to know. There is one very large data set, and this has been collected by a Japanese family since 1100. They do not have real measurements. Okay, what they have when certain flowers started to bloom, when certain, okay, bees and okay, insects appeared and things like that one. So based on what they wrote down in the diary, people try to attach numbers to it. Yeah? Okay, and it's hard to know, okay, whether those are real. So you don't have the data there. Yeah.
I have a general question. Let's say, on this movement,
Uh-huh.
for example, in your experience, what is the dependence of tests on the movement? Because my impression, no, there is a lot of freedom when we choose the base, we choose the smoothing, and so on.
Yeah.
So my theory is that this freedom we have, that before it would vary to be like freedom of removing an observation or two.
Yeah, yeah, yeah.
Now we have a lot of freedom more. So I say, how tests are dependent on this freedom we have?
Okay, okay, so, okay, if you talk about the raw data, okay, we never smoothed the raw data, okay, so essentially we kept it how they are jumping up and down there, yeah? We didn't touch that one because there is the famous paper by Peter Hall and Ingrid and the Dutch name, okay, when they warn that roughly speaking, okay, you can smooth the data so much that you will not see anything out of it, yeah? Only thing what we use is always the raw data there because you just have to compute integrals there, yeah? Yeah. The issue is, of course, okay, so whenever you are computing these phi hats and things like that one, then because they are using methods coming from differential equations, okay, this is what the paper who did it, of course everything is over smoothed, okay, but this one here is, it looks, I would say, fine, and typically you do not have much control above it. Whenever I talk about, okay, how to choose those H there when you have the long run covariance, okay, operator there, okay, we do not know too much about it. Only thing what we have, that we have like some kind of method how to choose the smoothing parameter, okay, using the data set there. So this is essentially a database, and this worked out relatively well there. My feeling is, okay, because you have functions and things like that one, okay, doing the choosing the wrong age there, okay, this is not as bad as in case of chaos univariate data there, yeah? So somehow, because you are computing integrals, okay, computing integrals in some sense is smoothing, okay? Even if you have very, very bad functions there, when you integrate it, you will get something, okay, which will be smoother there. So this is not as serious, yeah, but this is a very, very good question, is essentially how to do this type of things, yeah.
Well, thank you very much.
Thank you very much for having me.